We're going to now discuss a method called reduction of order. And the name of this method is a little bit unintuitive. If I had to call it anything, I would call it construction of linearly independent set of functions, which would seem more appropriate. Nevertheless, this is the name of the method. And the central question we're asking for this method is, so we're starting with this problem. If we have a non-trivial solution y1, okay, non-trivial meaning non-zero, of the homogeneous differential equation that we see here, it's linear, on the interval I, with of course the standard assumptions that a2 does not equal 0 on I and that the coefficients are continuous on I. So here's the question. Can we build another linearly independent solution y2 from y1? Okay, so we start with one solution to the second order homogeneous linear differential equation, and we're asking, can we get a second linearly independent solution from y1? Okay. So to discuss linear independence just a tiny bit, if the ratio y2 over y1 is constant, then we know that y2 and y1 would be linearly dependent. Okay. Of course, we could use the Wronskian, but we've studied this and we know that if this ratio is constant, in other words, one is a constant multiple of another, then they're linearly dependent. So we're going to take this ratio and set it equal to this function u of x, okay? Where we're seeking this function u of x, which isn't constant. Okay, that's where we start off. We start off with this basic form, okay? We're going to assume that y2, this linearly independent solution, linearly independent from y1, is equal to this function u of x, okay, times y1 of x. This is the beginning assumption. Now we're going to take our differential equation here and we're going to put it in standard form, okay? So we're left with this differential equation in standard form. Of course, p and q are continuous, and we could divide by a2 because a2 is non-zero, and so we put it in standard form, and we're going to give this equation the label asterisk, okay, just to cite it in future theorems. Then if y2 equal to y1 times equal to u times y1 is a constant solution, or not a constant, but is a solution, we would have this derivative, right, for y2. You just take the derivative there and you get this product rule. And then you take the derivative of that and you get more product rules, and you could find that y2 double prime is equal to what you see there. Now we're going to plug that into our differential equation in standard form. So 0 is the right hand side, okay, and it's equal to y2 double prime plus p. So we're just plugging in y2 into the differential equation. We're imposing the condition that it is a solution. We're going to see what that condition implies. So we plug in what we found for y2 double prime and y2 prime into our differential equation. For example, here, this is just y2. This here is y2 prime, right? And this is y2 double prime, okay, the second derivative. And this here is just y2, okay? And we simplify, we gather terms based on u, okay, the derivatives of u. So this term has u double prime, u prime, and u. And notice something about the coefficient of u. It has the same form as above here. So we know that this coefficient is 0 by virtue of y1 being a solution of the differential equation in asterisk. Okay? That's our assumption. We start with a solution and we are looking for a linearly independent solution from that one. Okay? So using the fact that y sub 1 is a solution, we have this is 0 and this whole factor is 0, and so we're left with that differential equation. Now, something to notice about this differential equation is it doesn't involve u. You have u double prime and u prime, okay? And now this is where this term reduction of order comes from. Because u doesn't show up, I mean, you could say that this is a second order differential equation as it is, but it's sort of trivially a second order differential equation. U's not showing up. So why don't we define a new variable w equal to u prime, and then now this exact same differential equation becomes a first order differential equation. Okay? Now, second order becomes first order. We've reduced the order, and now you know why this method is called reduction of order. Okay? And again, we could get away with this because the u's not showing up. Okay, so it's trivially a second order differential equation, and now the substance is really in this first order differential equation. We rewrite it, right? We divide by y1 and divide by w. We get this form right here, and we integrate. Okay, we have three different factors to integrate. This one turns into natural log of w. This one here, you can convince yourself that it's equal to natural log of y1 squared. You could pretty much do u substitution with u is equal to y1, and then du would be equal to y prime dx. Nevertheless, if you carry out that integral, you'll get this, and we move this guy to the other side. Okay? Now, from just adding natural logs, you could rewrite this as a product. Okay, that's just rule of natural logs, and then you exponentiate. Once you exponentiate, you have wy1 squared is equal to c1. Okay, and this c is just coming from the an integration constant there from integrating these. And so you'll get w is equal to this. Now, what is w? Well, w is u prime. Okay, w is u prime. So we want to come back to u now because that was what we were solving for before. We write that u prime is equal to w is equal to c1, y1 to the minus 2. That's just moving this y1 to the other side. Of course, that's, this negative just means that you're dividing by y1 squared when you do that in this expression. And we have this, of course, e to the, this term here is exactly the same. We could write it e as exp, or just like that. They're equivalent, same, just different syntax. And, well, we got u prime. And what are we going to do with u prime? We're going to integrate, okay? So we'll integrate to get u, and we'll have to integrate both sides. But u itself is what? I mean, what were we really after? We were after y2, and so you have y2 over y1 is equal to u, is equal to this integral, right? This is an integral with an integral inside, okay? Because this is the second integral. This is how we find u, okay? That first integral was how do we get w? So here's our second integration, and we solve for y2 by multiplying both sides by y1, and we get this general form right there for what y2 could be. And we're really after just one linearly independent function. Okay, this is a second order differential equation. So once we have two linearly independent functions, then we have a fundamental set. And so as long as we could just find one, we're fine. So why don't we just simplify things by assuming C1 is equal to 1 and C2 is equal to 0, and we end up with this final form. Again, no need for the generality. All we're looking for is one linearly independent function, and we could check that what we found here is indeed linearly independent from y1, in that we have a set of two functions that are linearly independent. We have this fundamental set for that homogeneous differential equation. So how do we check linear independence? And mind you, we know that y2 is a solution because we've assumed it up here. Okay? We impose this. All right? So we know that y2 is a solution, and now we could check that it's linearly independent from y1 by using the Wronskian. If you plug in y2 over here and you plug in the derivatives, after doing some math, you'll come with the determinant of this is equal to e to the negative integral p dx, and that's non-zero. The exponential is never 0, right? So that's non-zero, and because it's non-zero on the interval I that we were looking at, we have that y1 and y2 are linearly independent solutions of star, and they're actually a fundamental set. They both form the fundamental set, and that they could give us the general solution. So let's look at this theorem. So this theorem on the reduction of order, let y1 be a solution of the homogeneous differential equation asterisk that you saw above on an interval I, and that y1 of x does not equal 0. Okay, this has to be a non-trivial solution to work, of course, for all x and I. Then what we derived above is a second solution of asterisk on the interval I. Moreover, because y1 and y2 is a fundamental set, and we have a second order differential equation, two linearly independent functions, we then have this over here is a general solution of the homogeneous linear second order differential equation that you see right there, okay, in asterisk. And so we found our general solution. Of course, the key to all of this is that we had to have one solution, okay? It's like you start with a function, you use this method to get a linearly independent function, and because it's second order, you have two linearly independent functions. That's the fundamental set, and this is the general solution. So let's look at an example. So the function y1 equals x squared is a solution to this differential equation. And we want to find the general solution of the differential equation on the interval 0 to infinity. Notice how important here that we do not include 0. Okay, so this is an open interval. It's not inclusive of 0, because otherwise we would get the coefficient there being 0, and we can't use our powerful theorems on homogeneous linear differential equations. So we're going to put this differential equation in standard form. How? By dividing by x squared. This is the leading coefficient, so we divide by x squared, and we end up with this. We could identify p of x as negative 3 over x and q of x as 4 over x squared. And then we just basically use this equation. I mean, we don't have to. We could always start with, setting y2 equal to u y1, and then plugging it into the differential equation. Both methods work. Sometimes it's easier and faster to use the formula. Sometimes it's easier and faster to just recompute everything and go through the exact same steps that I've taken to get y2. So either way, but we have the formula, so let's just use it. Okay, here's the formula. Y1 is x squared. this is p, okay? We have to include the sign, so that's important. And we integrate this guy and we get 3 natural log of x. You move that 3 to an exponent of x. Okay, that's just standard rules of log. And of course we have this x squared squared because of y1 squared. So we have x to the 4th and we end up here. Now some people might be concerned, like, x to the 4th, that could be 0. Well, not really, because we're on the interval 0 to infinity. Okay, we're not including 0. And so integrating, we get this. And now the general solution, so we found y2, we found our linearly independent function from x squared. And so our general solution is here on the intervals 0 to infinity.